Let's start now then. So, okay, thanks for everyone for coming. Our speaker, Edem Fiatsonu, from Texas A&M, will give us a talk about effectiveness of Fluralaner treatment regimes for the control of Canine Chagas. I don't know how to pronounce that correctly. Maybe you will teach us then.
Yeah, that's Chagas disease. Yeah, that's it. Chagas.
Hey, let me leave the stage to you. Thank you.
You're welcome. All right. Thank you very much for the introduction. My name is Edem Fiatsonu from Texas A&M University, under the Department of Veterinary Integrative Biosciences, and Dr. Ndefo Emba happened to be my PI. I'm a graduate student anyway, from Ghana. So that, as you've already mentioned, the title of my talk is Effectiveness of Fluralaner Treatment Regimens for the Control of Canine Chagas Disease. And this is a mathematical modeling studies. So Chagas disease is one of the neglected tropical disease, mainly in Latin America and southern part of the United States of America. This disease was first discovered by Brazilian physician called Canine Chagas in 1909, and the causative organism for this particular disease is Trypanosoma cruzi. So Chagas disease is, people call it, or the other name is American trypanosomiasis. We have African trypanosomiasis, and this one is American trypanosomiasis. And it's being vectorized by an insect, a nocturnal insect called tritomine. So the tritomine, because of their feeding at nature, we call them, or we have a colloquial name, kissing bugs. So these kissing bugs are mostly found in this Latin America and some part of southern part of United States of America. And this insect mostly occurs also, we've realized that Texas is one of the states where we can find a lot of these tritomine bugs, and Chagas disease is as a hotspot now in Texas. So T. cruzi can cause a whole lot of health damages like cardiac damage, long-term heart disease in both animals and dogs and other mammals. So sometimes veterinarian always or sometimes mistaken Chagas disease for heartworm. So that's why it's important to study Chagas disease, and it has affected 6 to 10 million people, of which most of them don't know they have the disease because of the asymptomatic nature of Chagas disease. So I would like to talk about how it is being transmitted. So the transmission, and I would like to talk about the vector-borne aspect of it. So this infection or the parasite is being found in tritomine feces or poops and the intestines. So when these tritomine feed on its hosts, they use blood as their source of food. So when they feed, they defecate. The feeding process automatically does not infect or propagate the infection, but rather the infection or the parasite are from the poop. So if the host scratches accidentally, knowingly or unknowingly, they then infect the wound with these parasites. Also, how do tritomine also get infected? When they feed on these infected hosts, they get this parasite through the feeding. The other route of transmission is through food contamination. When they defecate around this food and we inject it, or a host injects it into their system, and these bugs are being infected with T. cruzi, then the host will also get an infection. And sometimes dogs also eat or feed on these tritomine bugs, or what we call kissing bugs. I would also like to look at the ecology and then some dynamics of these tritomine bugs. So most of them stay in the wild. They hide in the bush, and then some also stay in household or domestic. In the domestic, they try to hide in a crack or any place that they could colonize and then hide. And then during the night, they come out and feed on their host. So you could see that in the wild, they have variety of hosts that they feed on. And when you look at the domestic, we have human, they feed on human, and then they also feed on dogs and cats. One key thing about modeling is looking at not only the mathematical equations, but also how the dynamics of the whole system. So looking at this, we've realized that tritomines are abundant in some point in time within the year. They do not exist throughout the year. So there is some sort of seasonality in the activities of this tritomine. So this data is being collected by citizen scientists in Texas A&M, a group of researchers that works on Chagas disease. So they collected this data from 2012 to 2016, and they've realized that at each point in time, tritomine collection peak at around June, and then go down somewhere in November, and it dies off. And then you could see that the appearance or the flight of this tritomine bank correspond to their feeding habit or biting rate. It means anytime they come out, they purposely come out to feed, not to mate. So that's one key thing that we included in our model. So this Chagas disease in Texas among dogs, and this studies was done by one of our collaborators, Dr. Sarah Hamer Laboratory, where they tested a whole lot of animals to see the infection rate or the prevalence in these animals. And we've realized that dogs are the one most infected with T. cruzi. And they also work on some dog kennels, and they realized that some dog kennel has a prevalence from 6 to 13%, and some even have more than 50% prevalence of T. cruzi. So this is the prevalence I was talking about. So it ranges averaging from 5% to 30% in Texas. And since one thing about Chagas disease is now there's no available vaccine, it's very difficult to diagnose and treat, especially when it's in the chronic stage. So the best thing to cut transmission is to stop these kissing bags from feeding on their host, especially dog, because dog, we realize that dog is one of the sentinel who that propagate this infection even among humans. So the main aim of this research is to use mathematical model to evaluate the effectiveness of Fluralaner treatment regimen for the control of Canine Chagas disease, create different scenarios, or what we call counterfactual or what-if scenario, because math models allows us to create different scenarios and to inform best treatment regimen. So the main objective is one, we build mathematical model to describe this vector-host interaction. We investigate the efficacy of this drug at different transmission rate setting, because we've realized that some parts we have high transmission, some to very low, and then some medium transmission on dog population. And finally, we look at the interaction between the salvific or the wild and then the domestic setting. So basically, we have this, we build SI model, mechanistic model, depending or based on the disease status. So we know that Chagas, one, you are susceptible and infected, there's no recovery. So we have a simple SI model. So this model, we have three main models. A model we call base model, where seasonality is minimal or negligible. So we say there's no seasonality or impact of seasonality. And then you have a situation where there's an impact of seasonality of tritomine activities. And then the third model look at the spatial couple model, where we have the peri-domestic, and then the wild environment. So this parameter table. So this parameter table, most of the value were empirical data taken from literature, existing literature, and the one with asterisk, the kappa here, the carrying capacity of the tritomine was estimated where we put our model into equilibrium or put all the system into 0, and we estimated for kappa. And this phi here, we assume that some proportion of these adult tritomine feed at least one on dogs. Some of them will never feed on dog because we have other hosts like chicken, but chicken does not propagate infection. They are dead end hosts. So we believe that some of them will feed on dogs, some will not feed on dog on their entire life. So this is the diagram of whatever is happening in our model. So we have the diagram. We've divided the population of the tritomine into life stages. So we have the egg stage, we have the nymph stage, and then we have proportion that do not feed on dog, and then we have the proportion that interacted with the dog population. So this red mark or the red arrow shows the transmission of T. cruzi, where the transmission is occurring. Infected dog be bitten by uninfected bats, then the bats or the tritomine will automatically become infected, or there is a proportion or probability of that tritomine becoming infected with T. cruzi. So this is a nonlinear differential equation. The first one represents the egg stage. The second one is the youth stage with carrying capacity of with carrying capacity. So that's our system of nonlinear differential equation, of which we coded them in MATLAB and ran the simulation with our parameters that we have. We also use the model to estimate annual host transmission and then annual vector transmission based on those transmission settings. As I've already mentioned, we have the low, medium, and then high transmission setting for both dog and then tritomine prevalence. And one key thing is the behavior of tritomine bugs has two seasonality functions. We have the seasonality on the nymph maturation rates at time t, and then the transmission rates at time t. So the functional formula of this seasonality was informed from a literature where we had a data. Even looking at this data, you could see a stepwise function. So we use the data that we had to inform this particular function, which we later incorporated into our model. So we have a component called epsilon. So the epsilon is the relative activity level of the kissing bug during summer and fall compared to spring, because we've realized that it peaks at summer and then drop fall and then have that stepwise function and then go to 0 at spring or during spring. So that activity there is what we call the epsilon. And we also have the seasonality on transmission rate for both the tritomine and then the dog population as stated here. So we look at, so the main aim of this particular project is to evaluate the effectiveness of treating dog with this particular drug frequently, like different frequencies. So these studies were done in Brazil, and we modeled the result that they had into a functional form, which we later added to our model. So this is the result that they had. So looking at these results, they were able to achieve 100% mortality rates after allowing kissing bugs to feed on treated dog with this particular drug in a laboratory setting. So looking at this graph, you will see that for the first 7 months, they were able to achieve 100% mortality rates of tritomine bugs dying after feeding on dogs for some number of days. And After that, it drops to 66 and then goes to 0. And with this, they have number of days that it takes for the bags to die after feeding on the dogs. So if you could see, within the first day, the dog, within the first day, in the first and second months, the bags were able to, the treatment was able to kill the bags. And then the second days, it increased to the second days in the third month, and then, it increased to the 5th day for the 4th, 5th, 6th, and then 7th month. So after the 5th day, and then it drops to 66% in the 8th month, 57 in the 9th month, and so on. So with that, we just incorporate everything into our model. So that's what we have. We build it on the base model. So we just added these 2 compartments that keep track of all those bags that feed on dogs and their dynamics. So this ODE for the spatial couple model, of which because of time, I may not explain each line. I would like to escape and then go to the main resource. So this is our first simulation that we had for a single host model without seasonality. When I say without seasonality, we assume that the impact of seasonality is minimal. The impact is not that great, so we ignore it. So looking at the treating dog every 3 months, treating dog every 6 months, treating dog every 8, 9 months, and then every year. So looking at it, you could see that for there's much perturbation in the 12 months. The population of kissing back increase, drop, like that. So there's much perturbation compared to every 3 months. So every 3 months, you could see that the population density of the bars drop as indicated with a red mark. By looking at this, it keeps perturbation. So we just look at the average decrease of this population density in various treatment regimen. And you could also see the same thing happening in the spatial couple model, or where there is interaction of the wild and then the domestic setting. We also look at the reduction of T-cruisy prevalence in dog population given different treatment regimen. So this literally, I just transmitted everything into a table form because some people are good in dealing with numbers than looking at overall dynamics. So I just tried to extract everything into table form. So you could see that for the first 5 months, the population or the T-cruisy prevalence among dogs was reduced by 37.7% with this amount. And then 6 months, if dogs were to be treated 6 months, every 6 months without the impact of seasonality, this is how the T-cruisy prevalence will be reduced in a high setting. So this one, I just picked one setting, the highest setting for presentation purpose or for simplicity. And then you can see that it's small compared to 3 months when we are treating dogs every 3 months. And when you look at seasonality, a single host model with seasonality, you can also see that the treatment regimen perform better when there is no seasonality than when there is seasonality. You could see 36 against 37. And then it keeps dropping to 35 at when dogs were treated every 6 months and 9 months. And then at the same time, the same thing is happening when we have spatial couple model. So we also look at how the treatment was able to avert some infections. So in the single host model without seasonality, you could see that there's not much different in treating dog every 6 months and 3 months. So treating dog every 6 months and every 3 months is equally efficient or almost yielded the same results. So as you can see from low transmission setting, when the transmission setting is low, and then at the same time medium. But when you have high transmission setting, you could see that there is a marginal differences. But the differences pronounced when we have high transmission setting. So you could see from here that you could clearly see the performance of each frequency of treatment. The same thing applies to when there is seasonality. So the seasonality, you could see that there's perturbation. It's not constant. It's not like there's perturbation in the system. And the same thing applies to spatial couple. So in the spatial couple model, it is best to treat dog every 3 months compared to 6 months or 9 months. And we also look at if the activities of triatomine bugs varied. So our initial simulation, we assume epsilon, which is relative activity of these triatomine bugs, to be 0.25, 25% of the activities. And now we vary to 50%. So we are trying to look at what if we change epsilon, what will happen to the system? And we could see that the changes are insignificant, like very minimal. You could see the other one is just lying on it. You will not be able to differentiate between which one is 0.25 and which one is 5.0, sorry. And then we also look at the impact of migration rates. So since it's very difficult to calculate the migration rate of triatomine bugs from the domestic to the wild, we assume different rates and look at the different rate, the impact of the different rates on T. cruzi prevalence. And the last one happened to be the impact of, or the rate at which dogs were able to locate these poison or toxicated bugs and feed on them. Because some researchers believe that these dead triatomine bugs can be eaten by dogs if they see them or is being into their vicinity, they can feed on them. And even if they feed on them and these bugs are infected, they can inject this T. cruzi. So this is basically the impact of the dogs eating dead triatomine bug that's being poisoned by treated dogs or feeding on treated dogs. All right. This is our conclusion. So in everything, adding up everything, our main goal is to look at which regimen is best at which setting. So our analysis shows us that treating dogs every 3 months is the best, could be the best option. But I think it's based on the setting. So if there's the impact of seasonality is not that important, it's also economically good to treat dogs every 6 months because the differences in 3 months and a 6 months is minimal. But if you are close to a wild environment that is peri-domestic and then wild setting, it's good to treat dogs every 3 months because of the interaction of these triatomine bugs. And we also showed that Canine Chagas disease or canine and triatomine T. cruzi infection may be substantially averted when we regularly treated dogs with these drugs because they were able to run laboratory tests in somewhere in Brazil. So it means it can also be effective here when we treat dogs with this drug. And then in the low and the medium setting, treating dogs, as I've already mentioned, either 6 months or 3 months will equally reduce T. cruzi infection among dogs. And we also believe that if we're able to reduce T. cruzi infections in dogs, indirectly we are preventing from human cases as well because we don't have any vaccine for human for now. So that's why we are focusing on reducing it in dogs so that will reduce it in the entire population. And then the use of systematic insecticide or this drug may potentially increase. So it can also trigger the increase of T. cruzi infections, because if at the end of the day, these trichotomy feed on treated dogs and they die, and it's visible to dogs to also feed on, then it means they are going to inject more of this trichotomy that could be infected with T. cruzi. But this one, we don't know, there's no studies now to quantify whether dogs are going to locate these dead trichotomy and feed on. But this is just a counterfactual or what if scenario analysis that we are using our model to draw more insights into. So what should we do next? So at the end of the day, we suggest that further studies at a local scale are needed to better understand the potential impact of this regular use of Fluralaner treatments on increasing dog consumption of dead trichotomy, because now we don't know whether these dogs are going to feed on dead trichotomy. So I think, we think maybe there could be, I don't know whether it should be a laboratory studies that will intentionally kill trichotomy with these drugs and then make it visible to dogs whether they will feed on them or not. So I think a localized study like that will help. And also looking at our studies, we are more focused on American settings of homes, because when we go to Latin America, we have these rural areas where there are a lot of stray dogs. The way of treating domestic dogs will not be the same as treating stray dogs. Domestic dogs, you can get access to them, treat them every month, every 6 months, every 9 months. But stray dogs, there is no probability that when you treat the dog this month, within the next 3 months, you'll be able to locate the same dog and treat. So there's some sort of high percentage of these stray dogs triggering the transmission of T. cruzi, even where we have this system of treating dogs. So I think next studies should capture or should include the role of stray dogs in transmitting T. cruzi among this population. So this is a source of funding from Texas A&M, AgriLife, USDA, NIFA, and then American Kennel Club Canine Health Foundation that prevent, treat, and cure. And then this is my supervisor laboratory. For his laboratory, he's not working on animal model, but he using mathematical models to investigate transmission of infectious disease and then other public health interventions. And this is our collaborators, Dr. Sarah, who is specialist in Canine Chagas disease and then trichotomy bug surveillance, and Gabriel Hammer, and then this is my co-worker, co-author, Rahel Bosen, who is also a graduate student here. Thank you very much. Any question?
Thank you, Edem. Great talk. Any questions from our audience here? So, well, we have another get to know colleagues session that's going to happen in 20 seconds in the main room. But if anyone have questions, feel free to stay. And we will have another talk in this room after 30 minutes. But Edem, I have a question. So your treatment regime, you have every 3 months, 6 months, 9 months, and I'm happening to study something else, which we are gonna working on treatment on macaque, monkeys, basically. So one thing one of the treatment we play with is to do treatment every 1 month for the first 2 months, and then try it for every other 3 months. So I guess my question is there any toxic concerns you have such that the shortest interval you have is 3 months? Would more often treatment in the beginning and, you know, fewer treatment later would also be something to consider, just out of curiosity?
Okay, thank you very much for your question. So I will start from the end. So I think treatment, the month at which you start the treatment will be very important because of the seasonality nature of this whole system. But we are also considering the economic situation.
Yes.
Because when you ask people to treat dogs every month, some will not be able to afford. So we are capturing the masses, but in an effective way. So our treatment frequencies, they are based on data from laboratory studies.
I see.
That treating dogs for the first 3 months, they equally perform the same. So there's no need to treat every month, but it will be best to treat every 3 months or every 6 months.
Okay.
Or 9 months, depending on the seasonality nature of the trichotomy. Have I answered your question?
Just out of curiosity, how expensive it is for each treatment? Do you know by any chance?
I think I don't have the correct data, but I saw something. The drug is actually the sales at Amazon, I think $70-something. So it's just something like a capsule that it's like a chewing capsule that they give it to dogs to chew.
I see.
So yeah, so when they are treated within 3 months, and then any trichotomy that will feed on them will die, and then it will take them sometimes number of days, up to 5 days to die, but at the end they will die.
Okay.
So we just look at from economic situation that, okay, treating every dog every 3 months, every 6 months, and every 9 months or 10 months will do a 12 months. But the best regimen is 3 months. But if you cannot afford every 3 months and you are not living close to wild environments, you can equally treat 6 months for economic reason.
Yes.
Yeah.
Yes. Thank you. Thank you very much. Any other questions? Well, if not, I'm gonna turn this room off for like 20 minutes, so everybody can go to the main room to do the social, and we're gonna come back in a little bit later. Okay. Thank you, everyone.
Thank you.